Ja, wie Lego, ne?
Pretty much, I think.
You're just like standing right on the border doing
Now I kind of want to do that.
This is the first accelerator, synchrocyclotron, actual, built at CERN in 50s, upgraded 70s and stopped working in 90s. The first accelerator and the first building. I start a video presentation coming up on the wall and also on the accelerator. Watching this video, you can build your basics, how the accelerator is constructed and working.
Europe recovers from World War II. Many eminent scientists have left for the United States. European research is no longer world-class. To reconstruct European science, the visionary French physicist and Nobel Prize winner Louis de Broglie proposes the creation of a European laboratory that would be both a centre of excellence in physics and a motor for peace. His idea is taken up by American Nobel Prize winner Isidore Rabi, who together with Pierre Auger and Eduardo Amaldi convinced UNESCO to adopt this process. 18 months later, 12 European nations formally agreed to create the Conseil Européen pour la Recherche Nucléaire. The acronym CERN is born. Important decisions are taken in the first sessions of the new council. Geneva is chosen as the seat because of its central location in Europe and its international tradition. 2 accelerators are put forward, the synchrocyclotron and a much larger machine, the proton synchrotron. A new convention defines CERN's goals, stating that its research will have no concern with military requirements and that all its results should be made public. The CERN Convention is signed by 12 nations. Among the signatories are eminent physicists such as Werner Heisenberg. CERN comes into existence. 1954. On a site in Merin, a small village near Geneva, work for the new laboratory begins. Within a year, the farmland is transformed into a large complex of workshops, offices and buildings to house the new accelerators. The 5-meter thick walls of the synchrocyclotron building soon emerge, while the different parts of the new accelerators are manufactured in several European countries. The synchrocyclotron's magnet coils require particular care to pass through some of the Swiss villages on their way to Meran. As components arrive, they are assembled with great precision. Everything starts to take shape. The synchrocyclotron emerges, piece by piece. Some 54 elements are put together for the magnet frame. A total of 2,000 tons of steam. Next, the 2 7.2-meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of two D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready, and CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with a target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. Two D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after one half turn. Meanwhile, the radio frequency generator reverses the polarity between the two electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a half turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now In 1957, young scientists from all over Europe arrive. Among them are Maria and Giuseppe Filippo. Giuseppe wants to study a short-lived particle called the pile. In 1957, there was a mystery surrounding the pile. Theory predicted that a direct decay into an electron and a neutrino should happen, but this had never been observed.
Phenomenology, only later on in 1957, when with the theory of Riemann theory, the practical basis. So the moment the absence of the pi decay was very critical. It was essentially a block for the physics to go through. It was it felt like a block. And there was at that time, in January 1958, that I thought that was the right moment to do this type of experiment.
Giuseppe and his team set up a clever experiment. The pions are stocked in an apparatus designed to study their subsequent decay. In 1958, only a few hours after they start the experiment, the first pictures show clear evidence for this rare decay.
I'm getting passionate. I was really excited, with a surprise that can't describe it. I mean, it was something essential, because something I was seeing something for the first time, as I've seen before.
Spread CERN's name around the world. Over the following years, scientists at the SC continued to make many important measurements on particles, atoms, and nuclei. 1967, a new idea takes shape called ISOLD, an isotope separation device. Protons from the synchrocyclotron collide with target nuclei that are split into short-lived fragments, which are then rapidly scrutinized in experiments. The study of such short-lived nuclei with too many or too few neutrons helps to understand how heavy elements are produced in exploding stars. The synchrocyclotron accelerates its last beams in December 1990. After 33 years of an exceptionally long and successful career, the SC is retired.
We felt that the synchrocyclotron had worked very well, much more longer, given what much more role than anybody ever expected. Because he renewed the field of physics, explored in the 33 years. He passed, explored many different fields and had been very useful.
Following the synchrocyclotron's construction, CERN built bigger and bigger accelerators. The proton synchrotron, the intersecting storage rings, the superproton synchrotron, the large electron-positron collider, and the Large Hadron Collider. Many important achievements were made, some of them being rewarded with the Nobel Prize. The drift chamber, which revolutionized particle detection. The cooling of particle beams. The discovery of the carriers of the weak interaction. And the Higgs boson, which proves the existence of the Brout-Englert Higgs field. In 1989, Tim Berners-Lee, while working at CERN, created the World Wide Web, which has since changed our world forever. The Large Hadron Collider will continue to run at higher energy and higher intensity, with more than 11,000 scientists from over 100 nationalities, hoping for new insights into the secrets of the universe.
I think that the curiosity and the need to do research is inside is a part of our humanity. So there will be always a CERN. So there will be certainly a future.
What started once as a vision for European science has grown into a unique model for global scientific and technological collaboration. CERN demonstrates how science can unite nations and contribute to a better world.
So please.
Okay.
I thought. Frick.
There are the also design Tesla working 3.8 Tesla, cooled minus 268.5 Celsius. Strong magnetic field produced by these toroidal magnets through propellants separates the particles according to their charges plus and minus produced after collision is 1. Each magnet is 25.3 meters long, 100 tons. The piece what you see outside is a prototype. So these are the major magnets used toroidal in the active state. Then different sub-detectors, making one big detector, doing different jobs about different particles produced. They have the wafer, they cut the wafer, electronics on top is bump bound. But this is a beam pipe, and around the beam pipe pixel 92 megapixels. And of silicon strip detectors, 6 million. And clean picture of the electromagnetic glory wave. If something goes red, they cannot switch off their sub-detector because they are part of total data taking system, but they can mask the problematic area. Still, millions of channels are good enough from analysis point of view. But They prepare request which is approved. It means beam dumps after 2 hours. They can go underground.
The Higgs boson takes us to the instant of creation itself.
And it stands with the great scientific discoveries of all time.
One big spike here in this region here. So zooming in this region.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that has happened in my lifetime.
The discovery of the Higgs boson was a key moment for science. The Higgs boson is a quantum ripple in a universal energy field that gives particles their mass. It was the last missing piece of the Standard Model. This model describes the basic building blocks that make up the world around us. By studying these particles and their interactions, scientists are learning about the structure and fate of our universe. The ATLAS experiment was built for just that purpose. It sits 100 meters beneath your feet on the Large Hadron Collider, or LHC. This is the most powerful particle accelerator in the world, bringing protons and ions nearly to the speed of light before smashing them together at the heart of ATLAS. Physicists then record what happens during these collisions, looking for signs of new particles or interactions. To see the smallest particles of the universe, you need enormous detectors. The ATLAS experiment is a complex machine the size of a 10-story apartment building, and it took over a decade to construct. It is made up of several layers of detectors, each designed to study different properties of particles. Monitoring this complex experiment and analyzing the data is a global collaboration of scientists. With research teams on every populated continent, the ATLAS collaboration is one of the largest scientific efforts ever accomplished. Whether they are at CERN or the Research Institute abroad, ATLAS members work together to analyze LHC data, operate the experiment, and even construct new detector pieces. Discovering the Higgs boson was just the beginning. From the smallest particles of light to the heaviest quarks, ATLAS scientists are studying the fundamental constituents of matter to better understand the rules behind their behavior. These measurements and discoveries have advanced our collective knowledge of the universe. While our understanding of the subatomic world has advanced rapidly over the past decades, there is still a lot left to discover. The Standard Model describes ordinary matter, but that only accounts for 5% of the known universe. The rest is made up of dark matter and dark energy. But what exactly are they? ATLAS researchers are looking for new particles and forces that could explain these mysteries. As scientists work to unravel the mysteries of the universe, they are also advancing technologies that change lives. From the World Wide Web to proton therapy, fundamental physics research has already had an impact on your everyday life. Where can it take us next?
Was ist hübsch,